Let's go over the runtime of Mergesort, this Mergesort operation that we came up with in the last video. And so I think I'm just going to go line by line here and kind of write down what the runtimes are for each line and then add them up. And so for this whole Mergesort method, we're going to denote the runtime for this entire method. The runtime to be capital T of n. So what capital T of n means, well, the big T stands for runtime, and the n stands for an input of size n. And so what we're going to say is we're going to go through each of these lines here and then look at the runtimes of each. Well, the first line is pretty straightforward. We check the length and we check that it's less than or equal to 1, and then we just return that one value. Each of these is a constant operation. It takes a constant amount of time to do each of those things, and so we're just going to denote that big O of 1. Otherwise, we're going to split D, our input array, in half, and assuming that we've picked the right data structures or maybe even just did this whole merge sort using pointers instead of actually moving around arrays. We can split this in half in constant time as well. And so what is the runtime of these two methods right here, or these two lines right here? Calling merge sort on A, this half of the array D, and calling merge sort on B, this other half of the array D. Well, we already came up with some symbols for the runtime of merge sort, right? And we already hammered down our notation that we wanted to use for the runtime of merge sort. So now, given that the runtime is represented by a capital T and the input of size n is represented by n, we can denote the runtime of this to be the runtime of merge sort on an input of size n over 2. I'm going to write that out explicitly. This is the runtime of merge sort on an input of size n over 2. Right. So likewise, this will be the same thing. And so what is the runtime here of merging these two guys? Well, recall that when we defined our merge function, what we did was we said we would look at the top of each deck of cards, and we would keep popping off or keep taking the smallest element. And so what ends up happening is that we have these two decks of cards, and we keep taking the top one, and we always just keep taking the top one until both are empty. In other words, another way to think about it is that we're iterating through both arrays. And since we're iterating through both arrays, each array, or at the end result of merging is that we've looped through each of the arrays. And you can look back at the code that we wrote for merge and kind of just confirm this. But at the end, we're going to have iterated through each array exactly as many times as their sizes. And so given that the two arrays that we've passed in here, sorted A and sorted B, are of size n over 2, if D is size n, then these two are size n over 2, then iterating through both will give us the equivalent of iterating through all elements in the original array D. In other words, we'll iterate through the first n over 2, and then the second n over 2 in array B. And so this overall is going to be O of n, right? We iterated O of n over 2 times here, and we'll iterate O of n over 2 times here. And just combining that, we'll get an O of n operation. And we'll just denote that outputting the result is an O of 1 operation. This technically isn't, I'm just taking a shortcut here. Some professors might opt to say this is O of n. Depends on whether you're returning by value or not. But for our purposes, O of 1 suffices. And so now what is the total runtime? Well, the total runtime is we're just going to add all of these guys. Right? T of n equals all of this. So I'm going to put the answer here. And I'm going to combine, or actually I'm just going to combine these two guys to be 2 T of n over 2 plus, well, constant plus constant plus constant gives you a constant. And then I'm just going to write this guy down here. And that is equal to, well, when you add a constant to an O of n, the O of n overtakes it. It grows asymptotically faster than the constant. And so this right here is our recurrence relation for Mergesort. Just to write it out, the runtime for Mergesort is the exact same as the runtime of doing Mergesort twice on arrays of half the input size plus some linear amount of work. And we're going to go ahead and analyze this in the next video.